So there's a whole class of types of motion that we haven't talked about, and that is going in a circle, right? So I want to introduce rotation. We'll just start by talking about rotational variables. So we need to imagine something that rotates. Let's make a line, you know? So here's a ruler so I can make a nice straight line. And there's a line. And let's imagine sometime later, and let's let this thing rotate around something. So I'm going to draw like a dot, and that'll be my axis of rotation. All right, and then sometime later, maybe this guy has rotated. That's not pretty. I would prefer it be a little prettier. Yeah, that's pretty good. Okay, my intention is for those lines to be the same length, and for this to be the same line just later in time, right? So let's relate a couple variables, or at least define a couple variables. So I've got a length of this guy. Sometimes we call it r for radius, right? Not every r we talk about in this class is actually radius, but this one specifically is. I can also talk about the angle here. And we've defined angles before in this class, but we're going to think about this critically. So we're going to call that angle theta. That's a Greek letter, right? And we can also talk about the length that the end of this, whatever it is, let's call it a rod, the length that this rod has traveled, which would be this like curvy thing here. We can call that S. That's arc length. Again, I don't mean the linear distance between the tips. I mean the actual distance that it passed, that the end of this traveled. Okay, so it turns out we can relate these variables. The arc length is theta times r. Okay. But so it looks like S is a length and R is a length. So what are the units on theta? Well, theta has no units. Theta is unitless, right? This is basically a fraction. Right? What do I mean by that? How's that really a fraction? Because I know you will look at an angle and you think, oh, that should be degrees, right? Well, yeah, a degree is one way to measure an angle. But if I plug a number there in degrees, let's say that's 30 degrees, right? It's probably let's say it's 30 degrees. I don't expect if I plug a 30 into this, I don't expect this equation to be true. So what are the units that would make that correct? Well, imagine this. What if I do a full rotation? So a full rotation. Then S is the circumference of a circle, right? If you do a full rotation, this goes all the way around. I can't draw the whole thing because I didn't leave myself space. Yeah, so this goes all the way around. So that's circumference. And remember that circumference, so it gets a C, is 2 pi r. Right? That's just mathematical geometric truth. Right? That the circumference of a circle is equal to 2 pi times the radius. Right? That's how we define pi, is the circle. That's one way to define pi. Okay. So then S is 2 pi, but S also equals theta r. So it looks like for a full rotation, theta is 2 pi. So that defines the full scale for this fraction, right? So when theta goes from 0 to 2 pi, that's radians. What we're used to is when theta goes from 0 to 360, that's degrees. Right? And again, all that's changing is what we call a full rotation. Right? It's a unit thing, which is funny because, again, theta is essentially a fraction. It's the portion of the circle that you've done. We could say let theta go from 0 to 1. You could do that. But then our equation for arc length would have to have a 2 pi in it as a conversion factor, right? So often we just leave theta in radians. All right. So because radians is this kind of unitless unit, we can kind of make it show up and disappear when we want. You'll see what I'm talking about in future examples. So this is why the radian is the SI unit for degrees. Sorry, not for degrees, for angle. Right? Okay. So let's think some more about this. So I've got this, make some of this go away. So I've got this arc that this thing is traveling. So let's define a couple things. We've got theta now. Oops. Theta is angular position. Right, and typically we call the positive x-axis we'll say equals theta equals 0. Let's not make it equals. Let's make it a colon. We typically call the positive x-axis 0. That's our origin, right? Just like for x and y motion, we define what x equals 0 is and y equals 0 is. That's where we put the origin of our axes. Here we're just saying, here's where we're to define theta equals 0 to be. And typically, motion that is counterclockwise is positive. Just like for the x-axis, we typically choose the right to be the positive direction. Here we're choosing counterclockwise motion to be the positive. Okay, so that's angular position. When we talk about change in angular position, this could be angular displacement. I can do better. All right, so that's just like theta final minus theta initial. What I've labeled here actually could be a delta theta, right? Because we're going from 0 to some non-zero point. Okay, so this looks familiar. This looks like things we've done in the past. And in fact, let me make some of this go away. In fact, we can remember, or right over here, that so delta theta is our angular displacement, and I can relate it to arc length with the radius. And if I complete that delta theta in some time, which I expect to, I could define an angular velocity. And often we use the Greek lowercase omega, so that's a curly w, right? That's a lowercase omega. This will be angular velocity. And just as we did for linear motion, we're going to define this as delta theta over delta t. And you can see a unit coming out of this pretty quickly. That if theta is in radians, then delta theta over delta t is in radians per second. That is the SI unit for angular velocity. And in fact, you can do you can do this. You can say the relationship between tangential velocity and angular velocity is very similar to angular position and arc length, right? So let's say we had an object actually doing this motion, right? So there's an object on this path. The tangential velocity, which is this guy. So we're assuming there's no motion in the radial direction, right? There's just a delta theta. The tangential velocity v sub t is omega times r. Okay, so far so good. If the angular velocity is not constant, right? If that's changing in time, changing velocity is an acceleration. You see, everything we've done for linear motion, we can do for rotation. And we're going to do that for the next couple chapters. All right, so alpha is what we use for angular acceleration. So we're just translating everything to Greek. All right, so naturally, angular acceleration is change in angular velocity over time. So delta omega over delta t. And strictly speaking, that's an average. The unit here, as you might expect, is radians per second squared. And the relationship to tangential acceleration, a sub t, is alpha times r. Okay, so we have definitions on the left. We have ways of getting from angular acceleration to tangential acceleration, angular velocity to tangential velocity. That's useful. So let's move forward. Let's think about one way that that rotational motion is different from linear motion is that rotational motion is cyclic, right? When you think about motion on the x-axis, you can just go on forever, right? X goes to infinity. But motion around some axis of rotation, you can do that forever, but you keep going back to where you keep tracing your path, right? So we can say this: rotational motion is cyclic, meaning it repeats itself, right, over and over and over. So if something repeats itself in some amount of time, we can define a variable that is the time to complete one rotation. We call this the period, and we use a capital T for that. Right, so the period of something is the time it takes to complete one cycle. You could also think, instead of period, you could think how many rotations happen per unit time. So the number of rotations per unit time. That's frequency. And we use a lowercase f for that. So time for one rotation is period. The SI unit for that is seconds at the time, so it's going to be seconds. And number of rotations per unit time, in this case per second, is frequency. Is frequency. So the unit for that, let's do this. The unit here is a second. The unit for frequency is actually inverse seconds, or sometimes we define that as hertz. Right, and it turns out period and frequency are related inversely. So period is 1 over frequency, and likewise, frequency is 1 over period. Finally, I can calculate period for some motion if I knew arc length and the amount of time it took to complete that arc length. Right? Sorry, that's not what I want. That's not what I want. What I want is tangential velocity. Sorry. There. Tangential velocity I can calculate with arc length divided by the amount of time. And if I choose a specific arc length, meaning the circumference, that is a specific time, which is the period. So that's useful. So I have the tangential velocity can be calculated with 2 pi r over t. Let's make the middle bit go away, just to make this nicer looking. And I can also write this as 2 pi r f. Finally, remember that tangential velocity is also omega times r. So if I divide an r out, I can get omega. And omega equals 2 pi over t, or 2 pi f. So we see that omega and frequency, so omega is angular velocity, and frequency are just related by this 2 pi, right? Because the units for frequency are inverse seconds, and the units for angular velocity are radians per second. So the only difference is a unit, right? And this 2 pi has units of radians, basically. So sometimes we call omega angular frequency because it's radians per second. So we will see all of these come into play in the near future.